Okay, welcome back. Now we are going to illustrate a half-life experiment. We're going to start with an isotope of cesium. It's a 55 is the atomic number, and then the atomic weight is 137. This isotope of cesium is unstable because it is a heavy cesium, right? And it will undergo beta decay, and beta decay is E -10, and then it's going to beta decay into barium, 56 atomic number, and then the weight is 137. The barium that it produces is an excited state of barium, and then the excited state of barium will undergo gamma decay, and this one has a half-life of 153 seconds. So naturally occurring cesium, heavy cesium, will undergo this beta decay in 30.1 years. So if we leave it alone, after 30 years, half of the cesium will have decayed to barium. That's what it means to say the half-life is 30 years. After one half-life, half of it will remain. But we're going to do so that this occurs quickly. And then I'll show you how we're going to do it. We're going to do it so that this occurs quickly. And then you got the barium that will flow out. And then our experiment will concentrate on the barium. And then the excited state barium will decay in 153 seconds. This is the equation of radioactive decay. This is the decay rate, R decay, as a function of time. This is equal to the original decay, 2 to the minus t over tau, where tau is 153 seconds. So what does that mean? When t is equal to 1 half-life, what will the decay rate be? Then you'll be equal to R0 to the minus 1, which is R0 over 2. That means the decay not only is the amount of the barium after one half-life decaying by half, right? But the decay rate is also decaying. That means the rate at which they're decaying is also decaying, right? So then after two half-lives, our decay is going to be equal to R0 to the minus 2, right? Because this is going to equal 2 half-lives. Then this is going to be 2 to the minus 2, and this will equal R0 over 4. And then after 3 half-lives, Rd will equal R0 to the minus 3. So then it's just going to be R0 over 8, and so on, right? So a half-life is defined as the rate at which the number of the original isotope decays by 2, and also the rate at which it's decaying also decays by 2. It goes down by 2. So let me show you here how we're going to do this. It contains cesium-137, and then it has a half-life of 30.1 years, right? And then what's going to happen is I'm going to put here on this side this acid, and then it's called here the spectrum techniques, and it's eluting solution for cesium-barium 137 isotope generator, and it contains 0.9% sodium chloride in 0.04 molar HCl. So what will happen is when I put this solution using that syringe, when I put it through the top of this, and then what will flow out is the barium. I'm going to make the barium come out of the cesium-barium mixture, and then what flows out will be the barium, and then I will put it here. That will be the barium liquid, and then that barium will decay using a gamma process, gamma ray decay. And then I'm going to be using this Geiger counter. It says Geiger-Müller counter, the Pasco. And then that will be connected to my GLX Explorer. And then it says here digital adapter that's connected to the Geiger counter. And then the Explorer GLX will be connected to the computer so that I could monitor the decay count of that element, and then I will be able to find out what the rate of decay is, and then I can plot that. Okay, so let's carry on with the experiment. And now I have put the Geiger counter right over the solution, and then I open the computer, I connect the GLX Explorer to the computer. This screen comes up and says pulse count. So then I'm going to decide here the constants. I'm going to decide how many seconds I want it to do the pulse count, every how many seconds. So you can pretty much choose anything. Let's put 30 here. Okay, so I'm going to put 30. Okay, and then we're done with that. Put this, put the pulse count where it says table, and then press start. So what's going to happen is I started the timer, at the 30-second mark, it's going to tell me at what rate this barium solution is decaying, what the decay rate is, R decay, at the 30-second mark. So you'll see over here the time, 30 seconds, then it's going to show you the decay rate. So 30 seconds, the decay rate is 1,837, right? We call that the activity of the radioactive decay. The activity at what rate they are decaying, 1,837 pulses per second at the 30-second mark. Then the next data point will be the 60-second mark. The decay rate will go down, right? Why? Because the number of barium isotopes that are active are also going down at the same rate. So their decay activity is also going down. So we'll see here at the 60-second mark, 1633. Okay, this is kind of also a random process. So sometimes you might actually see the numbers slightly go up, slightly go down. But then what we're going to do is generate a graph through these data points. And then using that graph, we're going to find the half-life of the decay. So you can see how this is working. And we are at the 9-minute 30-second mark. You can see we're at 570 seconds. And the decay has really went down, the decay rate. So it started at 1837, 1633, 1369, and it just keeps going down. 360, 363. After a while, you begin to notice it kind of plateaus. This is because this is an exponentially decreasing function. So the change in the decay is not as much from 360. You see how it went up? I mentioned earlier, this is a chaotic process, so it's not necessarily going to follow a good pattern. You might have, sometimes the drop might be a lot, 589 to 506, then 462, then 360, then it actually went up. But that's okay because we can make a function to fit between all these data points. We don't have to necessarily connect all the data points. Then 287, 281, 209, 218, it went up again. Then it was 196, 161, 138, and then we're basically past 10 minutes, 138 and 120. And you can actually even hear it too, that the decay rate has gone down. You see, the count rate of the Geiger counter is not counting as much, so you can hear the difference. Okay, so let's go one more data point. At the 11-minute mark, we can stop. Okay, so that's 102. So then we can say stop. Let's take these data points now and go to, we can either open Excel function, Microsoft Excel, or we can open a graph called Logger Pro. Either one will do. We have Logger Pro. And then I can take my data and then just copy paste it into Logger Pro. And I can copy it here. And then on the left side will be the time, and then on the right side will be the pulses. So you can see here that how it's sometimes jaggedy like that, but that's fine. We can now ask the Logger Pro, go over here, and we can do a curve fit. What kind of curve should fit through these data points? So we can go down. We can do an exponential fit. Exponential. The perfect fit would have been 2 to some power, right? The best option that I can see here is the one that says a 10 to the power bx. Then I can go in there and I can actually change the function and make it 2 to the power bx. So I can say here a 10 to the power bx, and look what it says here. It gives me an option to define the function, and I can go like this, and I can go in there and then change this to 2 to the power bx, and then we can say here base 2 exponent. Okay, and then we can choose that, define the function. Okay, we already did that. And then once we choose that, we can say here try fit. And then you see here how the fit fits nicely through the data points, through the middle of the data points. And we can say okay. So we have here, it's saying the best function that fits through those data points. You see how it goes on top of these data points. Okay, it goes on top of that, then it goes on the bottom of these red data points, and then it goes through the middle, And then it goes through the bottom of these data points, because it's trying to make the best fit curve through those data points. So sometimes you're going to fit above those data points, and sometimes you're going to be below those data points, and then sometimes you're going to be right through the middle of those data points, right? So then the best function is, I can put it here on the left. Okay, let's lit this up so we can see this left side of the board better. Okay. Now we have here y is the rate of decay, so that's r of t. Then you're going to have here a, which is 2137. And then of course there's an uncertainty. What does a mean? That means at t equals to 0, it's the prediction of what the decay rate would have been at t equals to 0. So at the 30-second mark, the decay rate was 1837. So at t equals to 0, it would have started out at 2137. But there's an uncertainty of 7190. So it might have been up to 2200. And then if you subtract 7190, it might have been something like 2000 something, right? So that's giving you the uncertainty. And then now it's saying 2 to the power what? And then this is the power negative 0.006933, right? And then that's the power of this. And then x is the t, right? The time. Right? And then, of course, the B also has an uncertainty, 0.0008174. So our result is 0.006933 plus or minus 0.0008174. Okay? So then, remember what the equation was? We have R of t was R0 2 to the power minus t over tau. So the half-life is the reciprocal of this number, right? So then what was my theoretical half-life? Was 153, right? So my percent error is going to be what? Within 5% error. But remember, there was an uncertainty here. B could have been either smaller or it could have been bigger. So what we can do is say, well, how much smaller could it have been? How much bigger could it have been, right? If we want to make our error a little bit less, we can say, well, the B could have been smaller by this much, right? If I reduce the value of the B, then my experimental half-life is actually bigger, right? So 0.006933, 0.006933, let's subtract 0.0008174 from that. Well, what does that mean? If I take the option of lowering this all the way down to the least possible value that it can be, this B value, right? Okay, then my experimental period is going to be 163, which is actually now larger than 153. Well, what does that mean? This data points allows me to go down all the way down to that value, so the data points are not very precise, but they still allow me to encompass the value of 153. So now my percent error is going to be what? Right? 6.88% error, but now on the other side. So my experimental result is larger than what I'm expecting to get. And then in the other case, my experimental result was smaller. So what does that mean? If I choose an appropriate value of this uncertainty, I can actually make my percent error 0, right? So that means my result is enough to establish the fact that the half-life is actually 153 is a reasonable result, because it is within my uncertainty, right? So if I keep doing this experiment over and over and over and over again, generate more numbers, and then of course this is the way that scientific experiments are done in the real world, is you conduct them over and over and over again until what happens is you get a more accurate reading of the B and you get a more smaller value of the uncertainty. When you get a more smaller value of the uncertainty, then your result is more and more sure. It's more and more precise until you finally establish what the half-life of that material is, right? So now how would this work in Excel, right? If we wanted to analyze the data on Excel, so how would that work? So if I take the data and I open up Excel and I copy paste it into Excel, Okay, then I say copy paste. Similar feature can be done on Excel. Now we're going to copy the data points. Then we're going to go insert and scatter plot. Okay. And so you can see the data points are kind of all over the place. But now we're going to ask for a curve fit. So we're going to go to layout, trend line, and then it says add more trend line options. So which option should we choose? Right? Exponential, logarithmics, polynomial, power, moving average. And so we're going to choose here, Excel gives me the option of exponential. That is the best type of fit. Choosing exponential, I'm going to go over here and say set the equation on the chart and display the R squared value. Okay, so let's make this big here. Okay, so of course the Y represents here the rate of decay. This represents the original value, right? 1960. So it is different from the value as predicted by the Logger Pro, right? Instead of 2137, it's 1960 would have been the original data. So this goes up like this, and the fit looks different too. You know, it goes down below these data points, right? Then it goes through the middle of these data points and so on. And of course, this one, e to the power negative 0.004, right? I'll make the font bigger so you guys can see it a little bit better. Okay, so I'm going to choose here 8 decimal places, and then say close. And so you can see here, R squared value 0.9955. So the R squared value says how good those points line up on that line. And then this one is the 1960 is the original rate count, and then this is the 0.004439. Now, is that similar to this? See, it's actually different, 0.004. But this is also base E. So how do we extract the half-life from that? So you have to do an extra step here. Okay, so let's. So then the R0 will cancel, and then you have here half e to the minus alpha t. Then you will take the natural log of both sides. Then you have here ln of half, that's negative ln of 2, and then ln of e to the minus, and then this will be negative alpha t, right? So if we don't have the function in terms of base 2, we can still extract the half-life from that data, but we have to do one more step. Then we have to say t is equal to ln of 2 divided by alpha. So whatever number is showing here, we just have to take ln of 2 and divide it by that number to give us the experimental half-life, right? So actually you can see that the result that this gave us was actually better. So there's maybe an advantage to Excel versus the Logger Pro. The Logger Pro gave us a result that was 144, but then it gave us an uncertainty in that data point which was able to encompass the 153. So our error was more, but our uncertainty was enough to explain that result. And we could have manipulated the result so that the error is actually 0. Here, it doesn't give us an uncertainty value for the alpha, but the result that it gives us is actually a better fit. So our percent error is less. So our percent error is going to be 100%. Both methods work really well, but they have their pros and cons, right? So 2% error, that's actually good. The other one was 5% error. So both of them work. This one just doesn't give you the uncertainty, but it gave you a better fit. Okay, so you can see the pros and cons on both. So this is really a good experiment to illustrate the nature of the half-life and to show that how it is exponentially decaying, to show you how to actually set up an experiment, do the graphs using 2 different programs, and then analyze that result and then get a percent error from that. Okay, thank you very much.